On February 19th, 2025, Microsoft announced its first topological quantum processor, the Majorana 1. I was invited to Azure Quantum Labs a week before that, and it was really hard to keep a secret, let me tell you. The day was kind of dazzling. Not only did I get to hold the Majorana chip in my hands, but I got to see a couple of systems running in the lab. And I got to see technical presentations by some of the smartest people I've come across in the field. So it was a really exciting day. And since I tweeted about it and created a thread about it, it's gotten over 1 million views and a lot of questions have come up. So I figured I'd do this little explainer video, sort of a Majorana FAQ, if you will, to see if I could answer some of the major questions that people have. So first of all, what is Majorana? As I said, it's their first QPU that's running on topological qubits. It's built from a new class of materials called a topoconductor, and Microsoft claims that it represents a breakthrough in quantum computing. So they're hoping to enable scalable, practical machines, fault-tolerant machines, what we've all been hoping for in the future. What makes Majorana 1 different from other quantum chips? Unlike traditional quantum chips that use superconducting or trapped ion qubits, Majorana 1 uses topological qubits based on Majorana 0 modes. So these qubits are inherently more stable and resistant to errors due to their topological protection. It potentially reduces the need for extensive error correction compared to other architectures. They're not going to be perfect qubits, but the hope is that they'll be low enough in errors that as we scale, we're not going to have to basically burn thousands of them just to create one logical qubit or error-corrected qubit. What are our Majorana 0 modes? These are quasiparticles theorized by Ettore Majorana in 1937. You should probably read up on him. He was a fascinating guy. After he came up with this paper, he disappeared about a year later, so no one really knows what happened to him. But I like to joke that when I went to see these things in person, I survived, so here I am. MZMs, or Majorana 0 modes, are unique because Majoranas are their own antiparticles. So in Majorana 1, these MZMs are created at the ends of the topological superconducting device I mentioned before, the topoconductor. These nanowires are made from indium arsenide and aluminum, cooled to near absolute zero, and tuned with magnetic fields. The MZMs are created when an electron's quantum state effectively splits with its properties shared between the two wires' ends, right? So if you can think of it as almost like each end of the wire has half of an electron. But that's not really what's happening. It's more of a superposition state. Its non-local pairing makes these antiparticles and gives them their unique stability. That sharing, which isn't literal, is what's protected and keeps the secret of the state. So you could think of it as deciding as whether the wire contains 1 million or 1,000,001 electrons. In Microsoft's Nature paper, they showed how these are measured through zero bias conductance peaks. And you can actually see that when the measurements are created, there's these two peaks showing whether it's 0 or 1, let's say, state. And that claims to have 99% fidelity, actually probably better than 99% fidelity. Critics argue it's not 100% proof of topological protection. I saw these qubits running, and these qubits can perform X and Z rotations. So if they haven't created a topological qubit, what's making these qubits operate? So, I mean, that's all I can say now. I can't exactly answer the critics fully, but I can claim that there has to be something running or these machines wouldn't be doing what they're doing, right? So how's the measurement actually performed? You could think of the wire as storing quantum information based on whether an odd or even number of electrons is present. So to take a measurement, a digital switch couples the ends of the nanowire to a quantum dot. Microwaves then reflect off the dot to tell the odd or even state very reliably to get those peaks. The resulting qubits are called tetrons because of the four-ended H-like shape that they're arrayed in. So there's like these two wires with a line between them, and then there's like a separation wire, and then they stack up like that. This should lead to better error correcting ratios of physical tetrons to logical qubits in the future because of their low error prone nature. Hopefully, from what Microsoft says, we can expect hundreds to 1 for rock solid logical qubits. And in the scaling paper, I'll put links in the comments. In the scaling paper, you can actually see how they go from the 4x2 array and move up to these giant arrays of tetrons that create logical qubits. And hopefully 1 million of these will fit on that tiny little thing that I held in my hand. So why is topological protection important? Topological protection means the qubits store information in a way that's less affected by environmental noise, like temperature fluctuations, electromagnetic interference. Because you're just protecting that little secret at the end of those wires, that's less of the actual thing that's being bombarded by particles or whatever at any given time. You could think of it like if you had a bridge and the sensitive parts were only the two support beams. If everything else could vibrate and whatever, and if it didn't affect the performance of the bridge because you got those two beams, you're good. So it's like a minimized area because of the topological structure that protects the information. The hope is that this stability, I mean, it's not a very scientific example, but it's the best I can think of in like the real world because we're not used to thinking on the quantum scale. So that stability can make Majorana's qubits more reliable and easier to scale. How many qubits does Majorana 1 have? Currently, Majorana 1 has 8 topological qubits. That's a 4x2 array of these tetrons with wires between them. But Microsoft designed its architecture with its system of traces and onboard controller to be able to scale up to 1 million qubits on a single chip. I believe that number is necessary to do some practical quantum computing applications. So the idea is you'd have 1 million of these tetrons, there would be error correction, you'd end up with, let's say, 1,000 logical qubits or so to get these devices that have like 1 error every million runs or so. And with that many qubits, you can do the advanced chemistry applications and things like that that they're interested in. Now, we can do interesting use cases with far fewer qubits than 1,000. In fact, once you have more than 50 or 100, you've already created a computing device that we've never seen before. You can't take a computer and with a state vector simulator create 50 or more qubits. So I like to say it like this. If you were to go back in time to the 80s and give someone an M4 MacBook, it might take them a few days to figure out how to use it. But once they did, they would have a device that has never existed before, and they'd be able to do amazing things with it. So it'd be kind of like that once we pass that barrier. What is a topoconductor? So it's a new type of material developed by Microsoft, combining indium arsenide, a semiconductor, and aluminum, a superconductor. It enables the creation of a topological superconducting state, forming those Majorana 0 modes at its ends. What can Majorana 1 do right now? As of the time of this video and the launch and the time I visited the lab, it's a proof of concept chip. So it can demonstrate the viability of topological qubits that led to the paper in Nature. It's not yet a fully functioning quantum computer. Again, 8 qubits, sort of showing the ability to do X and Z rotations. But if you do those in sequence, you end up with something like a Hadamard or other operations. But it shows promising stability and error resistance based on the numbers we've seen. Microsoft's going to use this to pave the way for larger scale systems. How does Majorana 1 address quantum computing challenges? Well, quantum computers struggle with qubit instability and error rates, right? That's what you hear about all the time. You hear about running machines multiple times, or what we call shots. Majorana 1's topological qubits are digitally controlled with those pulses we talked about earlier, simplifying the operations and improving stability. It makes it easier to scale them because you connect, you do the operation, you disconnect. So initial tests show 1% error rate in measurements. We're hoping for seeing coherence times go up and error rates to go down. It's exciting to think that once we pass that 10 to the 6 error rate, what these things might be capable of doing. When will Majorana 1 be commercially available? Microsoft didn't set an exact date. This is still a proof of concept research device. I expect that they're going to keep building it up and doing experiments and publishing papers based on what they do with it in the lab. But eventually, when it gets to that usable scale, let's say maybe 50 to 100 logical qubits, I'd imagine that they'll implement it into Azure Quantum. I think by 2030, from what I'm hearing, they're expecting to have a pretty usable system. They claim to be on the path towards building fault tolerance within years, not decades. So from what I'm seeing, it sounds like around 2030, you can expect this machine to be doing some pretty impressive things on Azure Quantum. In the meantime, this year, we're expecting to see 50 qubits on Azure Quantum through Atom Computing and their partnership and how they do error correction. So Microsoft is applying all these other learnings, both to other hardware vendors and also their own process in the future. What are the potential applications of Majorana 1? Well, if scaled to 1 million qubits, Majorana 1 could tackle complex problems like simulating chemistry reactions for drug discovery, designing self-healing materials for construction and manufacturing. Maybe we can figure out how to break down microplastics. Maybe we can capture carbon. There's all sorts of things you could do with materials science, because once you start getting into more complex molecules, they become exponentially more difficult for classical devices to simulate. Also expect this to work hand in hand with AI. We've already seen this kind of thing with Quantinium, where AI is working with HPC and quantum, come up with more optimal solutions. And of course, I would say that once we get in that many million qubit scale and then many thousand logical qubit scale, we could probably start cracking cryptocurrency and cryptography with these things too. But there's a lot of useful things to do before that doomsday scenario comes around for all quantum computing. How does Majorana 1 compare to Google's or IBM's quantum chips? Google's Willow chip and IBM's chips, they use superconducting transmon qubits, and Majorana 1, of course, uses topological. So even though Majorana 1 has fewer qubits now, again, the hope is that these qubits are more stable and will lead to better performance in the future with need for fewer error-correcting qubits. So who knows? If they get this right, Microsoft could end up reaching that million qubit milestone first. DARPA seems to believe in them because they selected 2 companies for the next round of their push towards fault-tolerant quantum computing. And those 2 are Microsoft's topological approach and PsiQuantum's optical approach. Is Majorana 1 proven to work? Microsoft published the research in Nature, showing they could create and measure MZMs. Some people remain skeptical. As I said earlier, though, something's making this processor work. So if they haven't succeeded at this, what's doing the computing? I don't know. But I guess we'll have to wait and see. That's how science works, right? Skeptic just means you have an open mind, truly, if you use it in the correct way. There's going to be peer review, and I'm sure there's going to be much more experimentation in the future. But again, the chip is running. What's next for Majorana 1? Well, Microsoft plans to refine the chip, reduce error rates further, and scale up the number of qubits. They're also working with DARPA, as I said, to build a fault-tolerant prototype to prove its practical utility in the coming years. These are some of the more common questions I got. Every once in a while, I would get a more hilarious question, so I can answer those too. Why do so many bald guys work in quantum physics? Well, I guess we shave our heads to cool our brains from all the overuse. No, that's actually an idea from a Ted Chiang short story called Understand. Another funny question I got was whether I was Lex Luthor. And while I am a DC fan, I am most certainly not Lex Luthor. So I hope this little explainer helped you understand a little bit more about Majorana 1 and how it works. I urge you to read the papers linked in the comments below. And I promise to answer as many questions in those comments as possible. So feel free to fire them off down there, and I'll do my best to get back to you.